Hi everyone, I'm Jay Lee, and I'm presenting the IdealNet, Adaptive Dual Self-Attention Network for Single Image Denoising. So in this talk, I will first talk about the relevant background and the motivations, and then our solution will be introduced in detail. Of course, the experimental result will be discussed after, and the talk will be concluded at the end. So the image denoising is one of the most common problems within the field of the image processing and the computer vision. It aims to remove the measurement noisy from the noisy images. Fundamentally, denoiser trained using a single noisy image tend to be more robust than most trained on entire dataset in coping with possible database, although several methods has been successfully developed, yet time-consuming. In addition, no existing appropriate applications to show that the add-on value of the image denoising method. In this work, we propose a self-supervised deep image denoiser which aims to make the denoiser only enforced on an attention region. This work achieved by two modules, the dual self-attention generative adversary module and the dual self-attention encoder-decoder module. In particular, the DSA-GAM is used to generate a single attention region, and the DSA-EDM is then to conduct denoising within the learned single attention region. For the DSA-GAM, in order to capture the first attention, we design the first attention blocks, which consists of 5 convolution layers with upsampling operation in between. The discriminator D contains 4 convolution layers, and each of which is with zero parting and liquid ReLU activation function. And then we propose the block A2B in DSA-GAM module to further precise the output of the A1B and generate the final dual self-attention region where the image denoising process will be enforced. In terms of the DSA-EDM, to achieve the computationally efficient image denoising, we deploy the DSA-EDM with a higher Poisson sampling probability and shadower encoder-decoder blocks to make a trade-off between the time complexity, particularly with respect to the model convergence speed and the performance scan. The Poisson drop-off operation were used to reduce the prediction variance. The performance of the proposed IdealNet is evaluated on 5 different tasks. The PSNR is adapted for all comparison over the learned dual self-attention region with respect to intensity difference. The first task is AWGN noise removal, as known as the blind Gaussian noise removal. This task was carried out on the 3 well-known datasets, the set 14, CBSD11, and the CBSD68. The table summarizes the comparison result with the noise level is valued as 25 and 50. The experimental result shows that first, our method significantly outperforms the KSVD. Secondly, our method is better than existing single image-based denoiser such as the self-to-self network on all noise levels. And finally, our proposed method still outperforms the leading non-learning method CBM3D. And here the figure shows one of the particular example with a noise level set as a 75. So it still shows our method predicted the best result. The second task is the real-world image noise removal. In this task, the PolyU dataset is applied. The results are summarized in this table here as well. So from here, we can observe that our method outperformed all dataset basis methods, including the CDN-CNN, IR-CNN, FDN-CNN, and the DDF-net, as well as one of the super resolution-based method, the MSR-ResNet. However, our method slightly less competitive compared to the state-of-the-art method S2S. Again, a particular example has also been provided here to illustrate the comparison result. As one of the objectives of this paper, we propose idea 9 as for reducing the image denoising time. The figure here shows that our method requires the shortest time to denoise a total of 11 images in the CBSD11 dataset. So we also compared idea 9 with Pioneer Single Image Denoiser DIP and the S2S. In terms of the model convergence rate, comparisons are performed in line with optimal PSNR performance obtained with respect to not only its corresponding iteration numbers but also the time required. So the figure attached here confirms that our method requires the smallest number of the training iterations and the shortest amount of the time to reach the optimal PSNR performance. As a downstream task of the image denoising, we adapt 100 sample testing images from the dark phase dataset, which were captured in low light and noisy conditions. The procedure of this task is that we first use MSRCR to enhance the lighting conditions, and then adapt different denoisers to remove the noises, and finally to conduct the phase detection process by using the retina net, which pre-trained on the wider phase dataset. Since the ground truth is not given in the dark phase dataset, we adopt the average precision of phase detection as a performance metric. So here, the two testing results are illustrated in this figure. In the first result, other methods can only detect at most 3 phases, but ours can detect 5 phases here. In second example, 11 phases has been detected by ours. That is better than the CNN one, which is 10 detected. So finally, to sum up, we propose a self-supervised deep image denoiser requiring a dual self-attention region within a single input noisy image to handle the possible data bias and dramatically reduce the computational cost. Secondly, we prove that a simplified encoder-decoder with a Poisson drop-off strategy could be better informed by the learned dual self-attention region in an ensemble learning manner to reduce the prediction variance. Finally, we show that the proposed denoising scheme significantly outperformed the existing state-of-the-art method for real-world phase detection in low light and noisy conditions. So, of course, our source code is publicly available now. So for more details, please read our paper. Thank you very much for your time.